Hi, so I'm going to talk about myself and Professor David Malone's paper on quantum multi-factor authentication. So in this paper, we looked at current classical multi-factor authentication schemes, we looked at existing quantum authentication schemes, and we propose our own quantum multi-factor authentication mechanism using a token. So first, I'll just review what classical multi-factor authentication exists. So the first type is SMS codes sent to your phone. So we're probably all quite familiar with these. Basically, the verifier will generate a code, send it to your phone, and then you'll be asked to enter that code into the browser. And this requires a user to type in the code. It also requires a second channel, so you need both a phone and you'll also need a telecommunication channel as well as an internet connection. And it's generally considered to be insecure. So it's quite easy to clone phone numbers. There's like no authentication really required in order to get a new phone number or change your phone number. And also telecommunications aren't encrypted in any way. So the second type is app-based authentication. So an organization might ask you to take a picture of a QR code or something like that and install an app on your phone in order to authenticate. So this involves the initial secret, which might be the QR code. And then each time you want to authenticate, you're asked to produce a code which is made up of the time and that initial secret. And then you enter this code in the browser or send it back to the verifier in some way. So again, it does require a user. It also requires additional software. So you need to have the app on your phone and you also need to have your phone with you. And if that initial secret is stolen, then the adversary that steals it can continue to authenticate as you because they'll be able to generate more codes pretending to be you. So the last type is a USB token. So this is based on asymmetric cryptography, and it's called asymmetric because the key that's used to encrypt will be different than the key that's used to decrypt. So in this case, the USB holds a private key. And at each authentication, the user will be sent a message or a secret that they'll have to encrypt with their private key. They can then send that encryption back to the server, and the server will have a public key for that user stored. And they'll decrypt it with the public key in order to check that it was correctly encrypted with the private key. So there's a relationship between the public and private keys, which means that the server doesn't actually need to store the private information. They don't need to store the private key, which is important because we don't need to send the private key like over an insecure internet connection each time. And we also aren't relying on the server to correctly store our key and not leak it. But it does require a USB. It's in theory possible to duplicate the USB or the private key on the USB, but it is very difficult. And the last thing then is that this public-private asymmetric cryptography is generally not quantum resistant. So it's based on mathematical algorithms that quantum computing can basically speed up the computation of. So we've come up with a quantum multi-factor authentication mechanism, which will use a quantum token. And the benefit of this will be that quantum properties help with security. And I'm going to go through those in a minute. But the main one is that we definitely won't be able to duplicate the token because we can't copy quantum bits. So I'm going to go through the different quantum terminology that we'll be using. So the first thing is a qubit. So a classical bit can take the value 0 or the value 1, but a quantum bit can take 0, 1, or any value on this sphere. If it's a value on the sphere and not just 0 or 1, then it's said to be in a superposition. And it's represented by a wave function. And this wave function says that with some probability alpha squared, when we measure it, it will go to 0. And with some probability beta squared, when we measure it, it will go to 1. And this superposition idea is actually what's meant by Schrodinger's cat. So when it's in superposition, we don't know what it is. In essence, it's both 0 and 1 at the same time, or at least some function of both. It's only when we measure it that it takes the value. So when we open the box, but measuring collapses the superposition, and then it will remain at the 0 and 1, or 1 that it's chosen. So that was measurements. So the next thing I'm going to talk about is just entanglement. So this is the idea that if we have 2 qubits and I entangle them, and then I send 1 qubit to the other side of the globe. If I measure the first qubit and I get a 1, then I know that if I measure the second qubit, I'll also get a 1. And this is weird because both these qubits are in superposition. And we said that when it's in superposition, it will return a 0 or 1 with some probability. It shouldn't be deterministic. It's unusual that when we measure the first one, we know we'll get the same result for the second one. But this has good applications for communication technology. And we'll basically be using entanglements to create different states with our systems. So the last one I want to talk about is just the no cloning theorem. And all this says is that we can't duplicate a quantum state, which is really useful for us as well, just in terms of the security of the token. So a simple quantum authentication mechanism might involve something like this. The server will create entangle bits and send 1 of each of those bits to Bob. And Bob will then measure the qubits. So these qubits are entangled and they're in superposition. So Bob will measure them. And for the first one, he gets 1, then 1 for the second, 0 for the third, and 1 for the last one. And this will create a code, which Bob will then send back to the server. And then on their end, the server will measure their half of the qubits. And if the measurements match the code that Bob sent, then Bob is authenticated. So there's a few problems with this. Firstly, every single authentication will require a quantum channel between the user and the server. And also, each time Bob wants to authenticate, the server will need to generate new qubits, which is not easy, basically, to generate qubits that are entangled and then send them. We also still need a secure classical channel if we want to secure the code that Bob is sending back. So our quantum authentication token relies on a quantum classical communication complexity problem that was used first by Dmitry Gavinsky in a online banking or quantum banking application, and we've adapted it for use in authentication. And essentially what that problem is says is it's possible to have a relationship between classical bits and quantum bits, qubits. And secondly, it says that a verifier can request measurements of these qubits, and using only the classical bits, they can verify that the user holds the relevant quantum bits. So in order to use these properties, we've to create a token as follows. So the server begins by choosing 4-bit strings, lots of them, and then they convert them to corresponding quantum registers. So this is the relationship we said we can have between classical strings and qubits. And it's using this HMP conversion, which is just the communication complexity problem. And in previous work, we showed how you can set up the quantum gates in order to have qubits and bits with this relationship. So once these qubits have been created, they can then be issued to Alice in the form of a token. So Alice now has the token and the server just has the classical bits. So Alice wants to authenticate, so she'll send her token ID to the server. The server will respond by telling her what registers they want her to measure. So if they want her to measure 1, 2, 4, 5, 7, and 8. Alice then says, okay, I'll measure a subset of these. And all this is saying is that we don't want one of them to have complete control over what actually gets measured. So they're kind of agreeing between them. Then the server will select what measurements should be done for each one of those registers. So just specific details on exactly what they want to be measured. And Alice will do these measurements. And she sends the results back to the server. And using the results of these measurements and just the classical strings that they hold, they're able to verify that Alice holds the correct quantum token. So S will authenticate A. So a few points on this mechanism. Firstly, the level of assurance depends on the number of measurements the verifier requests. And so the more measurements that Alice is asked to do, then the higher the probability that she is definitely the person that holds the correct token and not someone pretending. When the quantum register is selected for measurement, it can't be used again. So once it's measured, we collapse the superposition and then it can't be reused. And one benefit of this is actually that it means we don't need to use classical cryptography, because essentially once we've used it, it can't really be used again. But this does mean that there's a trade-off between the lifetime of the token and the level of assurance that's requested each time by the verifier. The authentication exchange does not require any quantum communication channel. So everything in this process was just classical communication between Alice and the server. And also the organization only needs to hold classical strings rather than quantum registers. And this is important because holding quantum registers corresponding to every single one of your users who might want to authenticate will lead to significant overhead for the organization. Whereas it's reasonable enough to ask Alice to hold on to one quantum token. However, in order to actually implement any of this, we do need quantum memories. So at the moment, quantum memories exist for maybe 11 seconds, and that's not long enough for a authentication token. So we are still waiting on quantum memories to exist fully. Thanks for listening. I hope you enjoyed the talk.